you will know where somebody has touched you and how with the pressure. So you have a temperature sensor, pressure sensor, and all that in your entire body, right? All that material. It is something everywhere senses, right? So you want to know or have a lot of sensors put in any structure too, so that you get all the information. Then after that, in our body, we also have some kind of a control, central control, which tells you, hey, you are doing good, or you are feeling good, you are not feeling good, right? So if you are not feeling good, you probably see what is the temperature of your body. The temperature goes up, then there is an alarm, okay? You say, I cannot go to work, you go to the doctor, right? So that's a health monitoring. So health monitoring is based on all your sensor mechanism, and then there is some kind of a central control. So this is our dream that, okay, at one time we'll make a structure like that it will automatically tell us that my remaining life is 10 more years. All right, or something. Structural health monitoring. So we want to know the health of the structure. For that, we will need. We always mimic our actually nature. You know, for creating any new device or anything, including your medical sciences, you basically mimic the nature, right? Whether even in the medical area, they want to find new drugs. They basically go back to our ancestors. They used to treat some of these things by something, right? And then they'll go in there and try to extract what is the chemical, then they go and make a allopathic medicine out of that, right? So essentially, so you have some picture of structural health monitoring and the triboluminescence, right? So what we did here was, this we found europium. It's a big name here. Europium tetrakis. It is dibenzoyl methyl triethyl ammonium. So this is triethyl ammonium, and this is europium, and this is like dibenzoyl methyl. Okay. So essentially, we call it europium B4TEA, and this is one of the brightest TL phosphors currently known. Right, we found out that, okay, this is the material which is, it gives us red-orange emission. You can see it in the daylight. Actually, in this room, I can crush that, and then you can see the light coming. They were not able to make this, so he approached me, and then we said, okay, we'll try. So we did it in a one Christmas break, and she's the one who kind of put her effort in. And it so happened, you know, we could make that material, and then we were not able to test it. We did not see whether it breaks here and then give the light. So when we sent it back to Washington, he was very excited. Hey, you guys did it, right? So that is how all the discoveries are happen by chance also. Actually, I mean, I can tell you many stories about what happened to me, but even otherwise, you know, all the discoveries happen. You are on the road, and some idea can strike, come your mind, and you can get it. So we have this. We are kind of writing some of the papers on that. So this synthesizing is very straightforward. You basically start with a hot solution containing 8 millimole of dibenzoyl methane, 8 millimole of triethylamine, and so much of absolute alcohol. You know, when I gave you that europium tetrakis, you can have a structure. So you know, this is one europium, so many hydrogen and all that chemistry, RDAs. Then you have to mix the same ratio of those elements, right? Some of you know that Avogadro number, right? That is a miracle number, that you know so many grams will have so many atoms of that. And then you can mix, you can basically, whatever you want to make, you can go to the engineering units and then weigh that much material. And that has approximately same number of atoms, right? That is how you create a new system, right? So here, this is in the engineering units, you know, 1 mole of anything you can find. And so you mix that, dissolve 2 millimoles of anhydrous. europium chloride. This anhydrous is a very, it makes it very expensive. There should not be any water. So they kind of give us in argon in a sealed tube, in a sealed glass tube. So it has to be immediately opened and then used. And it is a very expensive material. So we just did that, and we basically rest is chemistry. Some of this is like you mix it, heat it, and then keep it for that, and then you basically filter it and then take those crystals. Right? This is of course a basic method of synthesizing this. Then what we in there was some chloride which we had to remove. And then for removing that, it was a little tedious process. You have to remove that by repeated washing, right? So basically, it was a tedious process. So we wanted to find a cheaper method, and so that our yield will be more too. So we basically, this is again done by Kamala Bhatt. All the credit goes to her. We came up with this europium nitrate hexahydrate. We started, you see, like earlier it was like europium chloride. Okay, so you see here anhydrous europium chloride. Now in this, we started with europium nitrate hexahydrate. And then anhydrous ethanol, when we put in, we were able to get these crystals, right, and in more quantity. And we have this paper published in Materials Today in 2011. Right, one of our graduate students, Ross Fontenot and Kamala Bhatt, they are working, more or less, maybe half the time every day. All right, so basically we could find a new method of synthesizing this. This is how we kind of find out how much bright it is. So you imagine we have made some kind of this is a black box, blackened box, and this is a drop tower. So you can have some steel ball fall from here to this. This is your material sitting here. When it hits here, it is sitting on something like a plastic or acrylic sheet here, which is transparent. So when it hits here, the light comes, and this is 45 degrees. That's a normal thing of a periscope. So you basically, if your eyes are here, you can see how much light is coming out. Okay, and then he has recorded, and we have a lab view programs and stuff. So one of the things which we have. So essentially, we have made this system also to test the triboluminescent materials. So you can basically see that, and then some lab view code is written to find the results for publication. Right? So we have this system made here. And this beautiful drawing, the credit goes to Cheryl. Right? Cheryl is the one who came up with this drawing. We showed her the system, and she really did a very good job. We used to really scramble some other things, but somehow this really gives the whole entire picture of this, what we did.
Dr. Ross, can I ask you a question?
Yes.
The intensity of the light which you are recording there on the oscilloscope, is the intensity a function of the damage?
Intensity is a function of how, and basically how much.
And the next question is anybody tried to mix the thermoluminescent material with some other sensor material, for example, thermal sensor? So if you mix the two together and make a sensor out of it, then you have a double sensor. You have a thermal as well as structure.
That's a very good idea.
I don't know whether anybody has tried.
Yeah, we have not done. This is actually
And
new.
that will be serving double purpose.
Yeah, that's a good thing. I think that's a new direction that one can go in. Right. So once we have this, that is the advantage of this thing. All right. So basically, our results, we can say we found a new method which produces 82% more triboluminescent material This method, new method, produces more material due to the lack of washing required, takes less time. Decay time is this, and it is cheaper. And new method is brighter than the zinc sulfide manganese, which is the standard. Right, so basically on all of these we are kind of trying to write some paper which is written and it is in your handout. Okay, so now we also found morphine doping. Now if you dope with morphine, we found that, there is a paper written that this can increase TL by 8 times. Right, so it will make 8 times brighter if you dope it with morphine. But morphine is a Schedule 2 drug, and it is not easy to get. So I don't know. As of now, we were not able to do anything to. And this is of course a cartoon made by our students. They want to have some fun. So he said, okay, because it is if you use this, you may get there. So you don't want to use that. Okay, so essentially this is morphine when it was 8 times. Then the idea came, maybe why don't we find something which may do the same thing, right? So this is morphine, right? And this is piperine, and the same stoichiometric formula, same carbon, hydrogen, nitrogen, oxygen. Now that is the wonder of nature, right? All of us are made up of carbon, hydrogen, oxygen, but if numbers may be same, but if the structure is different, it all has different properties. It has earlier I was working on these nonlinear optical materials, and it was the same problem there. If we take a methane group from one side to the other, the melting point changes. All these property changes. And the same number of carbon, hydrogen, nitrogen, everything is same. But essentially the whole thing changes. And of course, I've tried my best, so it is very hard to really get a handle on what is happening here, right? If it is inorganic materials, you can understand a little bit better. But with the organics, I think we just, as of now, I don't know, we don't understand. At least I don't. But so this is the same formula for both. But for piperine, it worked. Okay, we tried. Okay, maybe it will work. So for the piperine, we got 2 kinds, food grade and 97%, and we did, and I'm going to give you the results of whatever we found. Right? It was done like europium nitrate procedural thing, and then we added this piperine solution, and we also found something that if you use less and more, this is what happens. So we kind of have in mind that we are, instead of morphine, we are using piperine. We thought it is about the same kind of material, so we just kind of did that.
So this piperine synthesized?
Piperine is available in the market. You can get that. Piperine is a material which you can buy that in the market. And it decreases the amount of time it takes for the crystals to come out of the solution. We found that. And it starts precipitation in a few minutes, and the full precipitation does not take no more than a few hours. The earlier thing used to take a day or so, right? So it will
Water solid piperine?
Yeah, piperine is water solid. They're all, we do it in the alcohol solution and all. And the fastest precipitation occurred using so many grams of piperine. Full precipitation takes less than 5 minutes. So it has made the process faster. And then there is a 97% piperine. It decreased the time it takes for the crystal to fully precipitate out of the solution. Changing the amount of piperine does not appear to show any significant change in the precipitation time. It remains constant till full